So we are delighted to have today with us Professor Michelle Greene from Barnard College at Columbia University. Professor Greene did her BS in psychobiology at the University of Southern California and then continued to a PhD in cognitive neuroscience at MIT under the supervision of Professor Aude Oliphant. She then did a postdoc at Harvard Medical School with Professor Jeremy Wolff. She continued to a second postdoc at the Department of Computer Science at Stanford, working with Professor Fei Li. Today, she's faculty in the psychology department at Barnard College at Columbia University. She has published many research papers, written 2 book chapters, given dozens of invited talks. She has and is serving in multiple editorial roles. She's the head of the Visual Cognition Lab at Barnard College. Her primary research goal is to understand the mechanisms that enable rapid, intelligent perception of our environment. She investigates how people process and make sense of visual information, from recognizing objects to navigating complex scenes. She combines approaches from machine learning, experimental psychology, and cognitive neuroscience, and integrates behavioral experiments, EEG, and deep learning to explore the neural and computational foundations of human vision. I must add that 2 years ago, she published an amazing dataset called the Visual Experience Dataset that includes over 200 recorded hours of first-person perspective of egocentric videos with integrated eye movements and odometry. This is an extremely important asset to our community, so I want to thank you, Michelle, for this. I'll stop here and welcome you, Michelle, to our seminar, and we are very happy to have you here to hear about your exciting research. Thank you for joining us.
Thank you, Sharon, for the lovely introduction. Thank you all for being here today. I'm just delighted to see old friends as well as some new friends. So Sharon mentioned the Visual Experience Dataset. This is what I will be chatting to you about, but to set the table for what this is and why I think we need this. I will say I situate my research in the problem of every time we open our eyes, we are faced with a very complex environment. We're moving our eyes about 3 times a second. And in each of these fixations, just a couple hundred milliseconds, we're able to get a vast amount of information. We know that this is a busy street scene. We know that this is a lot of buildings. And while computer vision systems often tend to end there, as humans, we get a lot more information. So we get a sense of the geometry, the structure, where the horizon line is, where there's some linear perspective, enclosing surfaces such as these buildings. And these cues allow us to know how easily we could navigate through this environment. It also allows us to make predictions about what we might see and where we might see it. So if you're trying to meet your friend for dinner, you're going to probably constrain your search to the sidewalks where people tend to be and spend comparatively little time looking up at the sky. And higher level aspects are available as well. You might know, just based on how you are as a person, whether you'd find yourself excited and exhilarated by the hustle and bustle, or intimidated and wanting to go back to your nice warm apartment because it's too crazy and too crowded. And, it's worth underscoring that, we get this from really impoverished knowledge. If you are looking at a given moment of this car and you're making sure it can safely turn while you're walking, all of your high resolution, all of your color vision is concentrated at that point of the car, with everything else being, very lower frequency, lower color. So a lot of these processes are deeply inferential. And so my research program more broadly is, how do we do this? And how do we do this so quickly? And so many of us in vision science ascribe to some version of this hypothesis that the visual system, through either some combination of evolution, early childhood development, personal experience, is tuned to the statistics of real-world scenes. And therefore, by being tuned to those statistics, can process them very efficiently. So if that's true, it becomes imperative to characterize what the world really looks like. What is the diet of the world as it hits our retina? And this is not a new idea. Basically, since the dawn of digital photography, we've become increasingly interested in this idea of natural scene statistics. These are publications over time. And, in early years, where one gets photographs tended to be in one of 2 sources. One could be stock photography, such as the Corel database, And those are lovely pictures. But I would assert, and this actually comes from some of my earlier work, that most of my daily input doesn't really look like this, right? It is far too stylized, beautiful, professional, so on and so forth. The alternative would be something like, taking extensive photographs of one's own environment. And I'm really drawn to this study by Belinda Bletch and colleagues where they put a little webcam on top of a cat and set the cat around in the forest. And you got to see beautiful shots taken from this cat's perspective, but it's a very limited set of environments and from the viewing proclivities of cat rather than a human being. In later years, the rise of social media, particularly photograph-based social media, really helped us give rise to massive scale image data sets. Cisco Systems estimates that about 90% of the data on the web are image-based, either photos or videos. And this allowed for the generation of data sets that are on the order of millions or tens of millions of images. Very famously, ImageNet really launched the deep learning revolution, but also more human-oriented database such as the Scene Understanding or Sun dataset or the Places dataset exists as well. And increasingly in cognitive neuroscience, similar approaches where a large-scale image dataset is shown to small numbers of viewers while doing brain scanning allows us to see how do brains respond systematically to the natural scene statistics of these data sets. So I know you all spoke with Kendrick Kay recently, who is part of the natural scenes data set. There's also the Bold 5000 from the Carnegie Mellon team and Martin Hebert's things. So as powerful as all of these are, I would argue that if we're taking seriously the problem of real world vision, there are still several gaps that exist between what vision is like to us out there in the real world and how it is even in these realistic data sets. And the first is about content. These are data sets that are sourced from the internet, and they're going to have the biases of the internet. So part of this talk will examine the similarities and differences in diagnostic features between things we sample from the real world versus things we sample from the internet. The second issue is perspective. If we are sampling from the internet, we're often trying to show the space in its entirety. But as we're interacting in these spaces, consider an internet kitchen and an egocentric view of one's kitchen. There are viewpoints that we experience that fall on our retinas that just simply don't exist in these data sets. And the final issue is that our real world vision is dynamic, and we need to consider what it looks like at the center of gaze. So the video on the left shows an egocentric video as a person is walking down the street, and the version of it on the right is cropping that video to where that person was looking at any given time. So, the right is really showing what is the visual diet as it hits that person's retina. So we need to take all of these things into perspective. So today I'll be telling you about the Visual Experience Dataset and some of the things that my group and my collaborators have been doing with it to fill these gaps. I'm going to start out by giving you just an overview of the dataset, what's in it, how it was created. And then I'm going to kind of rapid fire give you 3 projects in various states of completion that have been using this dataset. So I'll say I very much welcome questions, interaction. Because these are discrete projects, I'll probably pause after each one to see if there's any particular discussion points. But let's just dive right in. I want to start out especially with gratitude to create something that is over 240 hours of content certainly requires a village. And these are the folks that were responsible for this in my lab, including amazing administrative support, an army of student researchers, and an advisory team of other academics, Ben Ballas at NDSU and his team, Paul McNeilage and Mark Lasqua at University of Nevada, Reno, and their teams. It really required every single human to make this possible. But in general, the visual experience data set, it's about 240 hours of egocentric content. So content recorded from the first person perspective of about 60 users. It's broken up into several hundred sessions that are about, 15 to 20 minutes long on average. Roughly half of them are indoor activities, roughly half of them are outdoor. And it's very active data set. So more than half of it is ambulatory. We've tried to get as many different observers as was possible. So we have both children and adults, and we were sampling in 3 different locations throughout the United States that have very different visual image statistics. To get the eye movements for this, we had to create our own device, and by cobbling together a lot of different products. In order to get binocular eye tracking, we started with a pupil core from Pupil Labs. Some of you might be familiar with it. But the world camera on that product didn't have the largest spatial extent that we wanted. We really wanted to sample the entire visual field, or as much of it as would be possible. So we replaced the world camera with this chameleon from FLIR. And we also wanted to register eye movements relative to head movements. And so in order to understand head position, this Intel tracking camera gives accelerometry and 6 degree of freedom head locations. So we can register where people's eyes are relative to their heads, and then co-register it with this world camera. So all 3 of these sets of cameras, the eye tracking camera, the tracking camera, the world camera, need to be mounted with respect to each other rigidly and onto the observer. So cobbled together some 3D printed parts, put it on a helmet, and set people off into the world to wear it. So here's what this oh so fashionable object looks like with 1 me for scale. These can be plugged into a laptop. The laptop can go in a backpack, and you can set the observer off into the world to do just about everything that they do in the normal world. You can calibrate this thing largely in the same way that you would calibrate a normal eye tracker. We have a paper target. You can see this bullseye pattern. And we trained observers to imagine either a 4x4 or a 5x5 grid within the space that would be recorded by the camera, and to place that target at each of the locations while looking at the target. We then had an independent validation session where this checkerboard target was placed at each of these 16 or 25 points, and the process was repeated. Another nice advantage of the checkerboard calibration is it can calibrate the exact optical patterns within the camera and be used to calibrate some of those properties that might vary from device to device. Now, when you send people off into the real world when there's movement, the validated gaze error is going to be lower or higher, pardon me, on paper than it would be for your standard tabletop eye tracker. We've got roughly 40% of our sessions have less than 2 degrees of visual angle error, but the vast majority are under 5 degrees. This sounds poor, relative to what you get with tabletop eye tracking, but given the wide angle view of the camera, 2 degrees of visual angle is about 1.5% of the diagonal. It would look like this on top of the full frame, and 5 degrees of visual error would look like this. So in terms of what your eye tracking needs are, it's good for finding, where the gaze was it on an object versus off? If you needed something that was more precise, like are you looking at the nose or the eyes of a face, there are going to be fewer sessions that are going to be amenable to that. Here are just some examples of things that you might find within the data set. So being out and about in public, riding transportation, walking on city streets, exploring museums, watching sports games. Cooking was another popular category, and it's really interesting to consider all of the sub actions that go into cooking, whether it's chopping, stirring, finding pots and pans, manipulating those objects, measuring ingredients, things of that nature. Playing sports of various natures. So, even things that were as vigorous as tennis and table tennis, soccer, were available to our participants. And we also had a fair number of musicians. So if you're interested in things like playing music, reading music, collaboration among musicians, there are sessions for you there as well. exploring different parts of the great outdoors in different parts of the United States where this was recorded. I had a set of undergrads label each and every bit of these videos at 5-second increments with, where was this recorded in terms of basic level scene category, and what were people doing? And this is a word cloud representing the different locations that were filmed across the data set. And there's a fair number of them. As well as the types of activities, and this gets a little bit smaller because the number of activities were rather heterogeneous. So this was released in 2024. If you want to get it, and I hope it's valuable to you in your research, the World and I videos and annotations are available on Databrary. If you're interested in our pre-computed gaze processing results, they're at the Open Science Framework. And this is just because Databrary doesn't support NumPy arrays and things that aren't videos or CSV files. Our code that processes the gaze, maintains privacy, a whole bunch of other things is available at GitHub. And the paper that describes the data set in more detail was published at the Journal of Vision. So that's just the first overview of the data set, what it is. And as I said, what I'd like to do for the remainder of the talk is what have we been determining what we've been learning from the data set. But given that it's a kind of natural place to pause, I'm happy to take any particular questions about the data set itself before we continue.
Michelle,
Yes.
how usable are single frames? Are they is
In general, very useful. There are frames with motion blur, for example, so those do need to be filtered out. But in a lot of I don't have hard numbers, Jeremy, but yeah, I've been using a lot with single frames and it's been great. Okay, fabulous. So let's talk about some real world diagnostic features. And the question here is, to what extent do the data sets that we have, these large scale data sets that I mentioned in the beginning, how representative are they of lived visual experience? So each of these data sets that I describe was created with the same general process that one gets a set of terms from the dictionary or dictionary equivalent. So all of the objects one wants to sample or all of the scene categories. You go to the web and search for and download each of those terms, and then download all of the objects that match those terms, and then use crowd workers such as on Amazon Mechanical Turk to verify that each of the images you downloaded was in fact a member of those categories. It's worth noting that this procedure has been critiqued by folks in AI ethics because bias really does emerge in each of these steps. So your list of items to download might contain offensive terms or slang terms that could be used in an offensive manner. And of course, the internet itself is a filter. Things that go on the internet were interesting enough to be on the internet as determined by someone. So it filters by what, who, and how things are represented on the internet. And the correctness of these labels depends on the knowledge and cultural competence of the crowd workers doing the verification. This has been discussed at length. I'm going to address really this second bit, which is, does that internet as a filter fundamentally change the image statistics of what we experience? It's very well known that we represent ourselves in a different way on the internet compared to real life, that we filter out the most talented and beautiful parts of our lives while leaving maybe the messy middle. And there are also cultural parts of the internet that favor certain types of content over others. So when I'm on the internet, I see far more cute animals and delicious food than I probably happen to see in my daily life on any given day. And our lived experience, if we're taking samples of it, is less glamorous, messier, more crowded. And the question is, how much of this is a difference that makes a difference? Namely, could we use, when we consider AI that's been trained with images like you're seeing on the top, Does it generalize to images that we've actually seen in the bottom? What are the similarities and what are the differences? So in this work, I'm taking 3 different data sets of things that were sampled from the real world. One is the visual experience data set itself. This middle row is a set of text message images. So I did experience sampling, asking people to send me images of where they are in any given point in time from their telephones. So if one is worried that this wide angle lens from the VDB might create some optical distortions, that itself is difficult. These are from cell phones, so they're going to be more similar to what you see on the web. And the third was a set that was created from my Barnard lab, where we took a very professional 45 megapixel camera shot in the RAW with a tripod, but we're also capturing items from the real world. So these are all captured from the world instead of the internet. And we want to say, like, to what extent do computer vision systems, both convolutional neural nets as well as transformer models, how do they perform on samples from the wild? So we're going to take all of these samples from the wild, present them to pre-trained networks, and then assess how well they do. One metric that I'm going to use here is called category entropy. This might not be known to you, but for a lot of these systems, their output is some discrete probability distribution over categories. And one can imagine a really confident system that would predict very high probability for a category, hopefully the correct category, and very low probability everywhere else. On the other end of the scale, a maximally confused system might estimate that every category is equally probable. This can be captured with the notion of entropy, where a higher score reflects more uncertainty. And the more confident robot, this entropy would approach 0. So here's this. Places and Sun are 2 internet-derived data sets. The visual experience data set and the text message sets are 2 from in the wild. And I'll be plotting entropy here on the y-axis. And again, higher is worse. So chance would be up here at 8.5 bits. Perfect performance would be at 0. Here are 3 kind of more traditional convolutional neural networks. And while it's unsurprising that deeper, more sophisticated networks do better, they have lower scores, what I'd like to draw your attention to is this persistent gap between these 2 internet-derived data sets as compared to the experience-derived data sets. So these pre-trained networks are doing worse on things that are sampled from the real world compared to things that are sampled from the internet. Entropy is a really sensitive metric. If we were to translate this into accuracy and break it down by private spaces and public spaces, we can see that the accuracy on private spaces is almost negligible. That fewer than 1% of these images were correctly classified as the top guess by these systems. So it's really, really quite bad. The question becomes, well, why is that? And I think it's worth looking at some qualitative examples here. So here are 2 kitchens from the Sun data set. Here are 2 kitchens from the visual experience data set. And these Sun images were both correctly classified as a kitchen. And the rainbow overlay here are the gradients with respect to that decision. So these hotspots are locations in the image that were particularly important for calling it a kitchen. And so these counter surfaces are very important in both images. Perhaps some of the textures related to metal and wood that seem very, very common. Now, by contrast, the VDB images were both misclassified. The kitchen at the top was called a cockpit, and I think it's very interesting that the pixels that were driving that were all of these photographs and takeout menus and invites that were affixed to the fridge. And if you look at the refrigerators in the Sun data set, they are devoid of the kind of bric-a-brac that we tend to put in our houses. And this is because these internet data sets are real estate images, Ethan Allen decorating, things that show kind of the best and most aspirational aspects of how we want to live, rather than the messiness of how we actually live. Similarly, if we consider this kitchen at the bottom, A bunch of ingredients are dragged out because this is a session where the person is in the middle of cooking. And so the sheer clutter is causing the network, perhaps to call it an attic. And if you compare that to these sun data set images, you can see that neither of these kitchens are in the process of having cooking being done in them. So on the internet, we never use our kitchens. In the real world, we're using our kitchens. And these are different diagnostic features that are really not being captured in computer vision. You might be saying, yeah, Michelle, but these are convolutional neural networks. These are comparatively old. They're 10 to 15 years old now. What about some multimodal large language models, transformer architectures? And I agree. I think we should test that. So I took 3 internet-derived data sets, the ADE 20K, Places and Sun, the 3 in the wild data sets that I was describing to you earlier. And we gave them to GPT-4. And what we found there was that there's still a giant explanatory gap, even in a GPT architecture, between what can be done from the internet images versus what can be done in the wild images. And that's invariant to the optical characteristics of the camera, the text messages, and the professional camera, were also equivalently bad as well. So what we can say here is that internet trained computer vision is really missing a lot of the diagnostic features that are common to real world images, and that we need to take those image statistics seriously. I see Sarit has their hand up. Yeah.
Sarit, do you want to have
Go ahead.
Sorry. Yes, I wanted to ask whether this is related to the type of view in the images that you took, because it was kind of distorted because of the large angle. So if you have an experienced data set that is a regular camera, will you have the same effect?
Yeah, great question. So I was worried about that too, right? The text message images were taken from people's telephones, so they don't have the wide angle view. And this PITW, that stands for Places in the Wild, this was a professional camera, a 45 megapixel camera, with no optical distortion at all. So you've got 3 different cameras all showing the same different pattern. So it's not just the wide angle view from the VDB. But yeah, really good question. Aaron, I also see your hand.
Yeah, thank you so much. I hope that you hear me. I may have missed, how did you calculate the entropy? Because when you're talking about DNNs and entropy, we have quite of a huge distribution changes. And how did you consider that factor that you right now? It was clear that you have quite a different mislabeling there. And I was wondering, how did you come up with that entropy?
Yeah, absolutely. So I took the 365 categories that were from the Places taxonomy. And you ask each system to provide a discrete probability distribution over that. So what's the probability that it's an abbey or a church or a street or a kitchen or so on and so forth. And so you compute entropy over that distribution. And so if you've got a system that is putting all of its probability into one category, with negligible over here, that's going to be a very low entropy value. And as it gets closer to a uniform estimation across all of these categories, so in other words, that it's estimated equal probability across all categories, that would be the maximum. Wonderful. Happy to take any other questions about this project before we dive into the second project.
So I have a question. I mean, I thought to leave all of my questions to the end, but I will ask if you are able to compare this. I mean, we assume probably that humans would do the classification almost perfectly, but I wonder if that's really the case. I mean, I don't know if they will be able to do a 365 alternative force choice, but just labeling them, would they be much higher than for example, the those artificial results, say
Yeah, no, this is a great question, and I'm going to break it down into kind of 2 sub questions. I think if we gave people unlimited time, they're giving definitions of all the categories, the performance would be at ceiling. Some of the work that my students are doing right now actually is looking, when we give them a reduced amount of time, do they have advantages for these internet derived scenes? Because in some sense they are very prototypical. They have professional lighting, they have, very canonical views, arbitrary views of how you might have been looking, when you're cooking something in your kitchen, might be harder to see at a glance. Alternatively, because it's, what we see from our normal world, maybe it's easier. So it's an open question. So we're looking at this both behaviorally as well as EEG responses over time. So we're hoping to have an answer to that soon, but TBD.
Okay, great. Great. Thank you.
Okay, beautiful. So second question is, how do we use these image statistics? How do they guide our perceptual performance? We speak a lot about this idea of a visual diet. And so these are visualizations of just where particular objects have been found within different data sets, showing their spatial location distributions, visualized either as dots or heat maps or objects relative to other objects. And this is all great, but the actual lived experience of our visual diet is relative to our center of gaze. So in all of these cases, including my own work, not only are we looking at the statistics of these internet scenes, but we're not looking at them in a gaze-centered way. Work by Oric has kind of gone one step closer to that by putting a webcam on people and looking at like what is the diet of the size of faces they experience, and does that change as a function of whether that person was a familiar person to them or an unfamiliar person. And this is lovely, but no eye tracking was collected during this. And so one might wonder things like, intuitively, it seems like we experience most people in an upright orientation that would put their head above their hands most of the time. So is it a robust statistic of our experience that faces are seen higher in the visual field than hands lower in the visual field? If that is a robust statistic, is that does that remain when we consider where it is relative to where people are gazing? And then third, are there individual differences that might be predicted by somebody's stature? So if you are a tall person, are you looking down upon different faces? If you're a more petite person, are you looking up at faces? And insofar as there are different locations where we experience hands and faces, does that predict sensitivity? Has the visual system tuned itself to be better at seeing faces where we tend to see faces and better at seeing hands where we tend to see hands? We took all of the frames of visual experience data sets. This is about 27 million frames. And we submitted them to MediaPipe. MediaPipe is a Google tool that has a hand detector and a face detector. And these heat maps show just from the world camera where were faces in the world, where were hands in the world. And perhaps not surprisingly, the faces were in fact seen higher than the hands. But interestingly, when we make it relative to the center of gaze, so here the fixation locations are in the center of these crops. And we're looking at where the hands and faces were relative to this gaze. It's still evident that faces are slightly above the gaze most of the time for most people, and hands are slightly below. So the question about individual differences and height is also interesting. Because we had children and adults, we had a wide range of heights within the visual experience data set. And so we wanted to break this down also in terms of height. Just giving you a sense of this, these are two observers that are walking through the exact same location. The observer on the left is 1.57 meters tall, they're rather petite. Observer on the right is 1.88 meters tall, so rather taller. And it's worth just looking at just how each of the surfaces within the same environment land very differently for these two observers. And one might imagine that their visual diet changes very much as a consequence of their difference in stature. So we examined the vertical position of where we found faces and hands relative to the observer height. And what's interesting is as our observers got taller and taller, the location of faces, and this is just all faces, not just the ones that are fixated, became lower and lower in the visual field. So the taller folks were in fact looking down at the shorter folks, and the shorter folks were in fact looking up at the taller folks. For hands, interestingly, the situation changed and reversed, such that the taller folks were seeing hands higher up in the visual field. For faces, this effect size was rather large, so each inch or 2.5 centimeters of additional height lowered face locations by over a degree of visual angle. So that's very interesting. Now, when we constrain it to just fixated faces and look at how this works relative to the center of gaze, we can see that the visual system stabilizes the result. And for faces, it even reverses a bit with our taller folks actually looking at the upper part of the face a little bit more. And part of, while hand fixation location is relatively invariant. Interestingly enough, that this also changes where observers tend to land within the bounding box of these objects, with faces trending a little bit above the fixated bounding box and hands trending a little bit below. So where you even land within the object depends on the object and where that object tends to be in the world. So this visual diet makes a lot of predictions, right? And these predictions are testable. So because faces are above hands, even when we account for gaze, you might expect higher sensitivity for faces in the upper visual field and higher sensitivity to hands in the lower visual field. And we might expect this to vary by height, with our taller observers being less sensitive to faces in the upper visual field because they're seeing faces down here, and the situation reversing for our more petite folks. Now, because this changes a little bit with our center of gaze, we're going to expect a stronger effect in the periphery. And to give you a sense for why that might be, imagine you're at this concert, maybe you're looking at this gentleman at the center. So his face will be centered, but all of the faces in the periphery will be relative to where they are to you and your height. And that will make them either higher or lower in the visual field. All right, so to test this, we took a set of faces, 200 unique faces, and a set of hands, 200 unique hands. All of these were varying in gender presentation, skin tone, decorative markings, so on and so forth. And we embedded each of these objects into skin toned 1/f noise at various locations within the image plane. And we provided observers with one of these images that always had an embedded target for 50 milliseconds, followed by an aggressive mask. And their task was simply to say, what was the embedded object within this, a hand or face? We ran this study while also recording the height of the observers, so we could see if the effect of these observers also then depended on their stature as well. Here are the overall categorization results. So when either hands or faces are presented at the center of gaze, we get the highest performance. And this is not very surprising. The observers were looking at the center anyway, they have the most acuity there. What is interesting is this location cross-category interaction, whereby when we consider the lower visual field, people were better at hands compared to faces. And in the upper visual field, people were better at faces compared to hands. So this would be as predicted from the visual diet. As I said, we also expected that the effect would be stronger in the periphery, and that there should be a height effect. So this is peripheral face detection as a function of height. And we can see that in the lower visual field, people performed better as they got taller. And this makes sense because the taller observers were looking down at faces. They have more experience of faces being lower in the visual field. By contrast, in the upper visual field, our shorter observers had the best performance, and performance dropped as observers became taller. So this did not occur for hands, but that would also be expected from the visual diet because the hand location was more invariant to height. So we didn't expect an effect there, and indeed we didn't see one. So all in all, we think this is cool that the individual object detection performance is predicted by your visual diet, and that visual diet is individual in terms of your own height and also where one tends to look as a function of height. Another natural pause point if anybody has questions about this part of the talk. I see Marissa has a question. Oh, Marissa,
Yes.
good morning.
Hi, I'm sorry I have bad internet, so I'm not putting my video on. But I just was wondering if what is the horizontally wise, where are these objects? So I couldn't see from the schema, so I see the upper lower difference, but what is the central visual field, or are they appearing anywhere
They
along
can
the
they
x-axis?
they can appear anywhere within the x-axis, and we've used horizontal eccentricity also as a covariate in all of this modeling.
Okay, and how far do they go?
Ooh, the entire stimulus is about 14 degrees of visual angle squared, I believe. Although I should have looked that up before the talk.
Okay, no, it's okay, thanks. I'll just ask you something else about that later, but thank you.
Yeah, thank you. All right. If there are no other questions, then I will continue to project number 3. So project number 3 is about the difference between eye movements as we might collect them in the laboratory versus what happens when we're out in the wild perambulating around. And so this is collaborative work with Bruce Hansen at Colgate University. And this is just a video example where I've cropped each fixation relative, or each part of the video relative to where the person was fixating. You can get a sense for, what was actually coming into the visual system of this person. And you might start to ask yourself, well, why is it that we look where we do? Is it being, driven by not trying to fall through these cracks? Is it curiosity about some of the ducks near the pond? Lots of different questions. And we've known for over 50 years, close to 70 years, that our tasks influence our gaze and where we tend to look. But computational models of gaze prediction rarely account for this. So, these models tend to come in 2 flavors. The saliency types of models, which ostensibly say where you look is what stands out from the rest of the image, having different orientations or colors or motion or so on and so forth. And yes, this was true in the early kind of legacy saliency models, but even more recent things like deep gaze still make that same basic assumption. Another class of models, a little bit newer, is that where we look is based on the meaning, that whatever local bits are recognizable and have meaning to us is where we're going to look. But importantly, both of these classes of models make an interesting, or have an interesting limitation, which is given the same visual input, regardless of whether you were in the scene trying to find your friend or bird watching or having a conversation with a colleague, that your pattern of gaze would be the exact same, so that the top-down effects, the task, would not matter. So we want to see both how do these models fare in the lab, but also how can we model some more task-specific semantics. So we took a subset of the Visual Experience Database where 12 observers were walking repeatedly around the same pond. And what becomes interesting about this is they did this throughout the entirety of 2022. And a lot of, as you can see here, seasonal differences, weather differences. In terms of image-driven model statistics, these are going to change quite a lot, but the task is remaining the same across all of these observers and all of these sessions. So it'll be interesting to see how these models fare with it. We're going to apply kind of a spatial GLM approach where we're trying to predict the gaze map from the individual observer as a function of, 2 of our saliency maps. So we can take the original Edie and Koch model as kind of a baseline or legacy. We can take the predictions of deep gaze 2E as something that's more state of the art. And we want to make sure that any of these will be, kind of our null model here, which is a center prior, that all other things being equal, we look at the center because that is strong tendency and an ocular motor response. And what we're going to measure is the amount of information gained per fixation relative to the center prior. So if there are 0 bits gained, it is equally good as the center prior. If it's negative, the center prior is beating it, which is not good. And if it's positive, it is contributing information about our gaze pattern that wouldn't be captured by the center prior. Interestingly enough, these saliency models, even deep gaze, were just not very good at predicting where people were looking within the visual experience data set when they were navigating. We didn't expect ED and Cope to do especially well. It is an old model, but what's interesting is that even deep gaze, as sophisticated as it is, actually performed far worse than even the legacy model. And it's worth noting that deep gaze is trained extensively on eye movement patterns from free viewing within chin rested on the desktop eye movements, and it appears that when people are being ambulatory, that those eye movements patterns change quite a lot. And so one of the things we want to do is to find a way to model this better. And what Bruce and I have been doing is to see the extent to which language can actually provide us these task-specific semantics. And so what we did was we took a separate set of scenes entirely independent from the VDB, and we had human observers write descriptions of those scenes that were relevant to navigation. So tell a person, here's a picture, tell a person how they should walk through the scene as if you're instructing a blind person. And we take these descriptions and we turn them into sentence embeddings. So they're just vectors of numbers. And we do a little bit of surgery on a ResNet, a convolutional neural network, such that rather than doing categorization as its top layer, it's now trying to predict this sentence embedding vector. So it's trying to predict a vector of the semantics of the scene. And so we train these models, and then through gradient methods, you can interrogate what are the pixels that contributed to these task-specific semantics at every single layer. And what's cool about this is once these models are trained, you can then present new images to them, such as this VDB frame, get a predicted sentence embedding, and then use that sentence embedding to generate a task-specific priority map. And so if this procedure captures task-specific semantics and those task-specific semantics capture what people are doing, then we'd expect more people to be gazing at these warmer, more yellow areas compared to the bluer areas. So we added this priority map into our spatial GLM. And fascinatingly, it was the only model of the models that we tried that had a positive information gain above the center prior. So beating both of the saliency maps as well. So a question becomes like, is this sort of behavior task specific, or is it about the fact that you're representing semantics that come from people? We trained another network. So this was on navigation related semantics. We trained another network about people's descriptions of the objects in the scene. And we tested that both against this VDB navigation set and the COCO Search 18 data set by Greg Selinsky and his colleagues. This is a data set where 10 observers did visual search for several different objects within the COCO data sets. And as expected, the navigation map did better in navigation tasks than the object map did. And when people were doing visual search, the object semantic map did much better than the navigation map. Also worth noting that in the COCO Search 18, the deep gaze also did quite well. And that's unsurprising because deep gaze was trained on eye movement data that are much closer to COCO Search 18 than to mobile eye tracking, the VDB. So this is something that we're really excited about, both because it's showing not only a limitation of very powerful models, even like deep gaze to explaining mobile eye tracking patterns, but the idea that we can start getting some leverage of what would be top-down task-specific modeling for eye movements. So in all, big picture is I started this talk with 3 persistent gaps that exist between real world vision and naturalistic vision as we tend to study it in the laboratory. One is about content, and I've tried to convince you that internet-derived content does not have the same diagnostic features as the real world, so we need to be studying the real world with samples from the real world. Another is about perspective, that when we're engaging in tasks in the real world, we have fundamentally different viewpoints of that. Those viewpoints reflect our lived individual visual diet and experience. We need to take those seriously. And finally, the vision is dynamic and gaze-centered and very task-specific. So we're not going through the world saying street, 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 office, office, office. We're navigating, we're searching, we're trying to find our friend, we're curious about the squirrel on the corner, and that we can capture these kinds of gaze, task-specific gaze, possibly through language. So again, thanks to everybody who contributed to the Visual Experience Dataset. Thanks to Ben and his collaboration with the Face and Hand project, to Bruce with the gaze prediction, the National Science Foundation more than ever for not only supporting the development of the VEDB, but these projects that have happened later, and everybody who came out to chat to me today.
Michelle, thank you so much. This was a really great talk, and I want to invite everybody to unmute yourself and give Michelle a big applause. It's really great. And are you happy to to take questions?
I am very happy to take questions, and
Okay.
I see that Jeremy has
Great.
his hand.
Yeah, but Jeremy, can I? Okay, I'm after Jeremy.
You
Jeremy,
can
you
go
go ahead. I'll be
first,
after you.
Sharon. This is your party.
Yeah, I know, but still, you know, I give you the honor to start, and I'll follow you.
Okay, so my question's about that last project where the center of gaze seems to be hugely important. And it makes me wonder whether, particularly under conditions of navigation, it's not the eye movements, it's the head movements that are important. And if you had a head scan path, which I suppose you do, if you have center of gaze, then your scan path is where the head's looking. Would it turn out that predicting eye movements just isn't where the action is, particularly when you're navigating?
Such a good question. When we do these gaze-centered clips of when people are walking, it's astounding. People are looking just straight down at the ground, even when it's dead flat, and they know it. And that surprised me. So like Mary Hayhoe had a bunch of, these mobile eye tracking results from trails and very rugged terrain. And I'm like, yeah, but if people are on the sidewalk, it's going to be easier. But it's not. And Joy Gang has some really interesting VR results that are showing that people are doing the same kind of thing. I agree with you, Jeremy, that the head position and the eyes relative to head position is likely a big part of this story. We've got the head movement data. I haven't done the co-registration to get those yet. I know Paul McNeilage and some of his students are doing some of the work assessing the statistics of head movements. But yeah, that's a hold on, but I agree with you. It's a really good question.
I'll continue. So again, I have quite a bit of questions, but I want to ask again about the models, because the models that you showed are basically, or most of the models, apart from the one that you actually initiated, are based on static images, and basically probably people or computers that were given information based on static, when your body is not endangered in any way, while people, when they're walking, although they know this path, they can be tripping, or there can be, I don't know, with a snake or a squirrel moving along, and they have to navigate their body. And actually, from my point of view, their body is like in danger in a way, even if they're not aware of that. So I think that there's a qualitative difference that vision undergoes when you actually start moving within the world. And so I wanted to, so I have a few questions about that. So first of all, I think this is a beautiful result showing the dissociation between, you know, what perceptual predictions would be and what actual action-based vision would prefer. And I also want to ask, because you said that the videos were cropped. You basically cropped the periphery, and it could be in a way that like if you look at time t-1 or t-2 or t-3, that would actually predict where you are looking at now. But these, like what happens in the periphery, and I have no idea, but I was wondering whether this there may be some peripheral information that would predict where you're looking at now, because, you know, there were saccades that were moving. So that's one idea. And another is related to really Mary Hayhoe's amazing studies as well, where she actually sees that there's some distribution where you are looking a lot of the time you're looking at 2 or 3 steps ahead. And so with that distance, if you're able to compute it or to estimate it to some extent in your videos, would that be a good prediction of where people would be looking? Yeah.
Yeah. I'm going to start from the backwards earlier. Yeah, so I'm also a huge fan of Mary's work. And one of the things that I think was really striking about what she's shown is that the more difficult the terrain is, the further out you're looking. And so I agree with you that that's, you know, kind of qualitatively, I've definitely seen that in these. I've tested a version of my model where I had people annotate where the person's next 10 steps would be within the video.
Wow.
That model does it incredibly well as well. So that speaks to your second point. And then Sharon, I forgot your first question. Please remind me.
Yeah, I was thinking about the periphery, whether you can use the information from the periphery to perhaps predict, like in time t-3 or 2 or whatever, to look at where the gaze was and to see whether this is actually predicting where the eyes, or sorry, to see what is happening in the periphery and to see if, you know, if that can predict it, whether it was some motion or something, or even in a secondary prediction, you know, not the first or major component, if that's also something that would be indicative of where the eyes would be moving to, like at the next. Yeah.
Such a good question. So yeah, I share your intuition that is clearly a source of guidance, and that probably depends on the spatial resolution necessary not only to recognize the object, but what that object's role is relative to your current task. I would love to operationalize that. 24 hours in a day, man. I wish there were more time.
Yeah, it's really great work. Thank you so much.
No, thank you. Anna.
Anna, do you want to? Yeah.
Yeah. So I had kind of a speculative question about the second part. So as you were talking about the differences in height and the eye movements kind of compensating for that, I started thinking about cortical selectivity over the lifespan. And I was wondering if, do you think that even if we did have relatively unchanging cortical selectivity, would your data argue that eye movements can kind of compensate for that more flexibly?
Yeah, this is super interesting, right? So one of the things that Ben Ballas pointed out to me are a number of decently recent studies looking at and what Marissa chimes in here, because some of them are hers, where the maturity of the visual system is actually quite late, right? Like well into adolescence. And it's, this is my wild speculation hat on, but a lot of that timing also corresponds with like a lot of very serious growth spurts in kids. So one might start imagining that, like, is it the fact that your own stature and your own visual system's recalibration to what that visual diet is, because your visual diet is actually changing rather rapidly, is what's delaying the visual system's maturity. I mean, again, correlational, absolutely speculative, but perhaps interesting speculation.
It could be both. Both things together could be possible.
Absolutely.
Yeah, so if I may just chime in, yes, indeed. we were surprised to see that the difference between the upper and the lower vertical meridian in visual cortex is not present at all in children. And we know that it is present in adults. And in adults, we've analyzed now like 7 different data sets or so, and it's quite consistent. But this difference is really driven mainly by the vertical meridian, and it decreases gradually, so that at intercardinal locations, you have no differences so far. So we've been puzzled by this for years. And of course, trying to relate to the visual diet is super interesting. And I've been talking to Mary Hay Ho and other people about this. But the height also, just recently we published a paper in which we see that the vertical meridian asymmetry does correlate with height if you go from children to adults, whereas the horizontal vertical asymmetry does not. So I think there's a serious, and we need a larger database to really then factor out age against height and so forth. But even height, factoring out age already, if you take a very large span from children to adults, we do have a significant correlation with the vertical meridian asymmetry.
Cool, thanks.
Sandra, you've got your...
Yeah, thank you. I'm a huge fan of the first project. It goes very much in a similar direction as a project I've recently worked on with Melissa. Even though much smaller, not on the scale of your project. But it very much resonates with me. You mentioned all these biases we know in the models that you discussed, and now also this apparent difficulties these models have with categorizing real-world scenes. So do you have any hope that this will change at any point? Is there any feasible alternative to using internet images, or are we just stuck with this for the next, I don't know how many years until we start sampling data systematically on large scales?
You know, I've got multiple thoughts about this. You know, there's from approaching that question from the technological point of view, we've got more tools now to do better than we ever did before. You know, mobile cameras are very accessible to, you know, basically any laboratory. I'd say, you know, very large scale data sets. I think Ego 4D, especially, you know, that was started by the UT Austin group and Meta. I mean, you know, it has truly massive amounts of egocentric video. So we're getting those data, and systems are being trained on that. I guess I find myself a little bit more worried in the broader scheme of whether we should. When we start sampling from people's actual worlds, that leads to you know, potential invasions of privacy and ethical concerns and things like that. I don't know. Maybe that's just my own self and my own squickiness, but it's a thing that I worry about. But in terms of being able to have the data and train the models, I think we're in a golden age.
But if I may, so at this point still, I mean, that golden age relies largely on these internet pictures, right?
Well, for legacy models, you know, I think a very valid critique of what I did in the first part was that many of those models and data sets are, you know, 8 or 10 years old at this point. So, you know, as models come online with, trained with, for example, Ego 4D, you know, we're getting those models. And so, yeah, I'd say, you know, we might be in a local minimum right now because, like, you know, kind of the internet peaked, but then now these experience sample things are not quite there, but I think we'll get there.
Thank you.
Thank you. Aaron?
Sorry, it was just follow up by the talk that you had with Sandra. So isn't it possible that with the resources and with such a data set that you have, we would be able to train new models? I mean, I do not see that quite unfeasible. I think it's quite feasible, specifically that you are sharing, that you have quite of data, everything. Have you ever thought of like let's revolutionize this ChatGPT, quite beautiful imaginary images, to make it as real, as messy as the real world is?
Yeah, no, sure. I've absolutely had that thought. You know, I think from chatting to people, there are folks in the computer vision community that are using the VUDB for that, as well as training next versions of things like deep gaze because they are acknowledging that mobile eye tracking is just kind of distributionally different from laboratory eye tracking. So yeah, I'd say, you know, these are happening, these are works in progress, and we should see stuff on it soon.
So to tap into your comment a minute ago, by the time you do get these sort of models that are based on more real data, are we even more doomed with a total inability to tell what is true and what is just created by your cool new model?
Yeah, I mean, so when I think about my big picture gloom, the potential for misinformation and disinformation is a big part of that gloom. Environmental concerns, labor concerns, and then I think I've been reading a lot within AI ethics, and so the question of, yeah, what do these foundation models give us beyond, you know, in terms of insight to the costs they incur? You know, I've got questions about that.
I'd like to suggest a collaboration between you, Michelle, and Jeremy. doing doing search tasks in the frames for Michelle's videos. That would be really interesting to see how humans, not machines, perform. You know, not with those clean 2D flat arrays, but you know, with like, you know, more just an idea.
I
But
think Michelle and I had that project going, but we had it going when we were doing, you know, when the computers were being done with purple crayon on a piece of paper or something. Maybe we should revisit our youth, Michelle.
I think we should revisit our youth, Jeremy.
And I also wanted to ask if you took, say, for example, kitchen, and you showed how different your like the real world kitchen inputs are relative to what is available on the net at the moment. So if you took, for example, all the, I don't know if it's thousands, tens of thousands, or millions of kitchen frames you have, and you would do some averaging, you know, because there was a study that did that, for example, with fire hose and stuff like, would you get something that people would classify as a kitchen? Or how many would you, like, you know, if you would vary parametrically the amount of random kitchen displays, would you get something that, when would you get something that would look like a kitchen? Or maybe you wouldn't get anything like that at all, because maybe it would, I'm just wondering whether there's some statistics that are common across these scenes, regardless of the, you know, giant variability that probably exists in relative to what exists on the, just an idea.
I have done this qualitatively. I haven't done the psychophysics that you suggest. But here's the thing that's interesting is that, you know, in internet drive scenes, because you know, the photographer was selecting the viewpoint, and they're selecting a very canonical viewpoint, that those canonical viewpoints are very self-similar. So when you average scenes together, you get something that looks very sensible.
Yeah.
When you take something from your egocentric perspective, where my head is moving and my eyes are moving, and, you know, especially when you make this gaze relative, I haven't been able to make sense out of any average from these in a way that you can for the internet derived images, because of the ways that it locks to that canonical viewpoint.
Interesting.
Yeah,
So
and it does things like, you know, the slopes of the power spectrum, view experience, and, you know, other things like that. I wish I'd included that slide, but
yeah, this, okay, just last thought, and we're gonna I was just thinking, I mean, we have a sense that we actually experience the, you know, the kitchen or everything in a very coherent manner, although in every frame we don't, or in every saccade, we actually don't get a very big, you know, great gist of the whole scene. But maybe it's because we have this accumulation across, you know, every, you know, time window. So I wonder what happens if you would do some, you know, panoramic view of 3, 4, I don't know what, saccades, and then examine if this, not just an idea, but I was wondering.
yeah,
It's very hypothetical.
it's a cool thought. It's a really cool thought, and yeah, I've also been kind of thinking about, yeah, ultimately you want to express one of these spaces in full 3D, right?
Yeah.
So not just what you're saying, but just, especially towards Jeremy's question of where the head is moving relative to the eyes, because those head movements can be enormous relative to the eye movements. And so
Yes.
modeling what's over here in the far left periphery and modeling over what's here in the far right periphery is going to be increasingly important. And so it's challenging, but yeah, I agree with what needs to be done.
So again, Michelle, I want to thank you so much for sharing this with us. This was a really interesting and fascinating talk, and I hope it's going to be followed up by lots of follow-up research. I mean, it's a great asset that I hope you and many of others in the community will be using. And thank you again for this wonderful talk. And next week we will have Keisuko Fukuda. He will be joining us in the seminar. So thank you, everybody. Thank you, Michelle, and have a lovely rest of the week.
Thank you, Sharon. Thank you, everybody. It was a great conversation.